Hi, these notes are over 4.4, the equidistance theorems. The essential question is, how can I use the relationship between equidistance and perpendicular bisection in proofs? So first we need to understand what the word equidistant means. It means just what it sounds like. Equa means equal. Distance is how far it is from one place to another or one point to another. So equidistant means when 2 points are the same distance from a third point. So, for example, if I had 2 points, they will be equidistant from each other when they are the same distance from a third point. So I would need to position that third point carefully. If I put my third point right in the middle of the 2 points, then the distance from one point to that third point and the distance from the other point to that third point will be congruent. Okay? If I put that third point maybe in another place, maybe I put that third point here, these points will still be equidistant from this other point. They'll be a different distance, but they'll still be equidistant from that third point. I can put that third point anywhere. I could put it way down here, and the 2 points are still going to be are still going to be the same distance from that third point. So really, I could put that point in a lot of different places. I could put it here, here. Okay, I could put it here. And if you think of all the places where you could put that third point, all those points actually fall on a line that is equidistant from both points. So that's kind of what we're going to be talking about. That line and those 2 points. These 2 points right here. Okay, so here's one of your theorems. It says if 2 points are equidistant, which means the same distance, from the endpoints of a segment, then the 2 points determine the angle bisector of that segment. The angle bisector is another segment that cuts the first segment in half at a right angle. It has to be both perpendicular and has to be both perpendicular and bisect the other segment. So there's 3 ways that this could look. We first need to start off with a segment. So we've got this segment, we've got this segment, and we've got this segment. So we're going to consider 3 different scenarios. Let's consider the first one. Let's read our thing again. If 2 points are equidistant from the endpoints of a segment. So we have 2 endpoints. The 2 points that are equidistant can be in 3 different locations. First of all, you could have 1 point above the segment and 1 point below the segment. Okay? The 2 points are equidistant from the endpoint. So this point is equidistant from this endpoint, and that same point is equidistant from the other endpoint. These 2 distances are the same. The second point could also be equidistant from the endpoints. It might be a different distance, but it too is equidistant from the endpoints. It says if this is the case, then the 2 points that I just drew determine the perpendicular bisector of that segment, which means if I connect those 2 points, let me try that again. If I connect those 2 points with a segment or a line, that line not only cuts that segment into 2 equal parts, it bisects it, but it also is perpendicular to it. It cuts it at a right angle. Okay? And of course, both of these would be right. Let's consider another scenario. So that's when 1 point is above the segment and 1 point is below the segment. Let's consider if they're both above the segment. Let's say one is up here and one is up here. The first point I just drew is equidistant from the endpoints. I can show that with my ticks. The second point that I drew is also equidistant from my endpoints. I could show that with 2 ticks. Okay? If this is the case, then according to this theorem, the 2 points determine the perpendicular bisector of that segment. If I connect those 2 points, it will not only cut this segment into 2 congruent parts, bisecting it, it will also make a right angle with that segment. Okay, so that's when the 2 points are on the same side of the segment. We looked at when the points are on opposite sides of the segment. Let's look at when one point is off the segment and the other point is right on the segment. These points have to both be equidistant from the endpoints. So this one is the same distance from both of the endpoints. And this one on the segment is the same distance from both of the endpoints. According to this theorem, if this is the case, then those 2 points, if I connect them, will be a perpendicular bisector to that segment. It will not only cut it into 2 equal halves, but it'll also cross it at a 90-degree angle. Okay? Here's a second theorem. This one is kind of the converse of the one we just read. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of that segment. So if you start off with a perpendicular bisector, then any point on that perpendicular bisector is the same distance from both ends of the segment that is bisected. So, for example, if I have a point on the perpendicular bisector of a segment, so here's my segment, here's a perpendicular bisector, it cuts this in half, and it makes a right angle with it. If I pick a point on this perpendicular bisector, let's say right here, okay, according to this theorem, that point is equidistant from the endpoints of that segment. So this distance and this distance are congruent. Hey, I could pick another point on there. Maybe I pick this point, or I pick this point, or I pick this point. These are all going to be equidistant from the endpoints because they all fall on the perpendicular bisector of this segment. Okay, kind of looks like a football. It's pretty cool. Okay, so let's try these theorems in a proof. We have this picture, kind of looks like a kite. Our givens are that AB and AD are congruent, and BC and CD are congruent. Okay, I've already written those in my proof. We're trying to prove that BE and ED are congruent. So if you look at what we've got two pairs of segments that are both congruent from these 2 points B and D. Okay, so our first theorem that we wrote down says that if 2 points are equidistant from the endpoints of a segment, they determine the perpendicular bisector of the segment. So from there, we could say that AE, that vertical line, is the perpendicular bisector of BD. Therefore, it makes a right angle with BD. And from there, we could also do some other things to get to the point where we could say that BE and ED are congruent. BE and ED are part of two other triangles, and I think we might have enough information to say those triangles are congruent, and therefore BE and ED are congruent by CPCTC. So let's go ahead and write down what we know. We know that because of these, because AB and AD are congruent, they're the same distance. Point A is the same distance from B and D, and point C is the same distance from B and D, then A and C determine the perpendicular bisector of BD. So this perpendicular bisector I'm talking about is right here. Okay? So let's go ahead and state that. AC is perpendicular bisector of BD, and I'm totally abbreviating here. We know that it's a perpendicular bisector because of that first theorem we wrote down. It says, if 2 points are equidistant from endpoints of segment. They determine the perpendicular bisector of segment. They determine perpendicular bisector of segment. It's a pretty long theorem. Okay, so let's go ahead and mark that. That already cuts BD into two halves. I can already see that BC and CD are congruent, so that's already marked on our picture. But because it's perpendicular, it's going to make a right angle, which really means that all four of these angles are right angles. If I look at the bottom two triangles, BCE and DCE, they already have one set of sides in common that are congruent, and they each have a right angle. I can also prove that CE is congruent to itself because of the reflexive property, and then from there, by SAS, I can say those two triangles are congruent. So let's go ahead and say that CE is congruent to itself because of the reflexive property. Hope I have enough room. So what we've got an S right here. That was our given. This given right here. We've got another S here. But we also need to say something about those right angles. We said we had a perpendicular bisector, but we haven't said that we've got right angles and that they're congruent. So we need to do that, and then we can go ahead and use SAS. So let's say angle BCE, and angle DCE are right. Because that's the definition of perpendicular. And then we can say that they're congruent because all right angles are congruent. BCE is congruent to angle DCE because if two angles are right, they are congruent. Okay, so that's our other A. So now, by SAS, we can say those two lower triangles are congruent. Triangle BEC is congruent to triangle DEC. And now that they're congruent, we can say that BE and ED are congruent because of CBCTC. They belong to two congruent triangles. So this guy and this guy are congruent. And that's our proof statement. So that's 4.4. Here are the problems that go with 4.4. If you'd like to try these and work ahead, feel free, but not necessary. See you in class.